Thank you. Please go ahead. You are muted. You are muted, sir. Prabhakar ji, you are muted. Please unmute yourself.
Okay. Yeah. Okay.
Fine. Good.
Okay. There is no substitute of the physical meeting actually. Okay, so this is the present day power sector scenario. If you see that this is the current capacity of 260 gigawatt, and out of this you see that most of the parts, more than 50%, is being covered by the coal, which is 60.1%. We have gas, hydrogen, hydropower, and then renewable energy. So if you talk of the renewable energy, you have the biomass, and then wind energy is completing about 8.6%. Solar is only 1.3%. Okay. So, and this is the projection up to 2030. You see that now we are 2022, and we have to work hard to reach this task. You can see that our task is to increase solar photovoltaic up to 11%, increasing wind energy up to 14%. So the target would be to move more towards the renewable energy sources, which are clean actually, and of course they are green and clean. So our topic, the concern with that, and then how we can approach that, and what are the progresses that have been made, we will see actually. So what are the renewable energy sources which are required nowadays? Of course, the clean energy can be reduced and replaced, cannot be exhausted. And this is the dependent, this is climatic parameters. This is, of course, one of the major things. And there are the challenges which are, these are the challenges which are required to meet before we think of the renewable energy sources. Now, they are the land acquisition, funding, economic policies, and everything. They are very, very important. Okay, because the coal are still very cheap, and it is very easy to burn coal and then get the sources. However, if you want to make the energy through the solar thermal, so you have to put a lot of money, a lot of energy towards to implement it. So these are the challenges we have to meet actually. So the renewable energy, as I said, that they are the solar energy, wind power, hydroelectricity, geothermal, and the biomass. These are the possibilities, and of course we, as I said, that we, before we implement it, we need to meet the challenges also. The question is, we are talking of the renewable energy. Why do we need this renewable actually? You see, why the important, we scientists, generally physicists, when we talk anything, we first think that why it is required and why it is happening. So why renewable? This is the big question. You see that the carbon emission, the dangerous, the gases which are harmful to the environment, when you move towards the kind of economic growth, then industrialization needs some inputs, and because of that you need to have the carbon emission. You see that because of this carbon emission and the hazardous gases which are emitted, the global warming, of course, you can see the polar ice cap melting. So, and this is the data which is showing the atmospheric CO2. You can see that it is increasing with the kind of, with almost exponential rate with the year wise actually. So our task would be to reduce it up to a certain level, so that we can maintain our society as well as the environment, which is very important point at the time to ponder of, to think of by we scientists. Okay. As I said that the renewable energy resources, one of them, which is the solar energy, basically. You see, the solar energy, why? It is abundance, and throughout the daytime you can get fewer maintenance problem, and breakdown. It does not pollute the environment, of course, because it is clean energy, no greenhouse gas emission, lesser running cost, no obvious health hazards. All these things is very, very important for the requirement, and the solar energy meets all these things. So before we think of that whether the solar energy is sufficient or not, I would just put a data in front of you. This is very encouraging actually. So let us talk of the sun. What is sun? So it has a radius of 10 to the power of 6 kilometer about. The outer temperature is roughly 6,000 Kelvin, 6,000 Kelvin, of course. The center temperature is a kind of 20 million Kelvin, and the rate of energy emission from the sun is 3.8 into 23 kilowatt. This means that 3.8 into 10 to the power of 23 kilojoule per second it is emitting energy. And this energy, you see that it is expanded in all the direction in a kind of spherical in the environment. Okay. And a very tiny fraction of this energy, you see that 3.10 to the power 23, a tiny fraction of energy is intercepted by the earth, which is about 1.7 into 10 to the power 14 kilowatt. Okay? And if you assume the world population as 10 billion, which is still less, actually we are about 7 billion, 10 billion with a total power need per person, let us say 10 kilowatt. Okay. So then we need 10 to the power of 11 kilowatt of energy to meet the requirement of whole world, actually, each and every person of the world. And let us say that we are using a device which has, let us say that only 1% of the total radiation which is received by Earth of this 10 power 14 is utilized by using a device which has only 10% efficiency. Then you see that, let us say 1% means this is 10 to the power of 12, and 10% of efficiency 10 to the power of 11. Okay, so we need exactly 10 to the power of 11 kilowatt energy to meet the requirement and need of each and every person on the earth. I am optimizing here. You can see that only 1% of earth is intercepted, the energy is intercepted by the earth, means utilized by the earth, and only we are using a device which has only 10% efficiency. So you see that this is very encouraging, of course, and we can be sure that the sun is the source of, and this is why we worship sun as a god, because it is the only source of the energy on the earth. So, but there are, of course, it is very encouraging, of course, but from the scientific point of view, from the science and economic point of view, of course, there are some problems which are physical, because most of the radiation are falling on the sea, on the mountain, on the desert, where population is not residing. We cannot use in the night, and these are the physical problem. We have the technological and socioeconomic limitation. Technological, as we said, that we need to have a device which has efficiency at least up to 10%. Any device when you use it is not durable for a longer time to keep its efficiency for a longer time at a high level. Economical level is, of course, there. We need money, lot of that. So this is the thing which we remember always while we talk of the sun. You see that the sun, as I said in the beginning, that it is the source of nearly all energy on the earth. So you see that you can collect solar radiation in two ways. It is a natural collection and the technological collection. So in the natural collection, you see that what we do, photosynthesis, the food which we eat, the animals eat, everyone use food that is generated from the photosynthesis. So the sun is the only source to generate this photosynthesis. The wind, actually, how the wind blows, you know that wind always, it is a fluid, it flows only with the difference in when there is a pressure difference. And how this pressure difference is created? It is created when there is a temperature difference. You know that the land is heated very fast and the water resources are heated very slow, like sea. So the always wind blows from the lower temperature to the higher temperature to the lower temperature. So during summer, the wind blows from the sea level to our earth level, because it is at higher temperature, and therefore pressure is reduced and the wind blows. So the wind energy is basically because of the solar radiation. The sun, if there is no sun, no wind will be there. Ocean temperature difference, of course, it creates, and then we have all tidal energy and these sources. This is the solar radiation. In fact, whatever fossil fuels you are using, they are basically the residues of the plants and the animals which died, I think, long millions years ago, and they are buried below the earth, and they are basically, the carbon is converted into, because of the high pressure, into the liquid, and this is the petroleum and diesels. They are natural gases. So they are also in the beginning, where those the plants and the animals, where did they get the energy? Of course, from the sun. So basically, this the fossil fuels also because of the solar energy only. It is not because of any other sources. Now, technological collection, you can collect it in a thermal power, like a thermal plate collector, where you convert energy into thermal energy in your house, in your in the swimming pool, and the warm water, warm liquid, fluid, oil, everything, the thermal conversion of the technological. We have photovoltaics, the electricity which you receive in your house through the solar panel, solar cells. Okay, so this is basically, you see that on the earth, especially on our earth, the sun is the only source of energy that we can utilize. Okay, so now I just said that there are, if you go back, the technological collection, we have thermal and the photovoltaics. I would cover the solar cell part, that is the photovoltaic, okay, and the materials required for that. Okay, what is photovoltaic effect? As I said, that I will also discuss some fundamental physics of the photovoltaic effect, how the solar cells are working. So you see that this is simply a kind of photoelectric effect, where light is falling on a surface of a metal and the electron is emitted. This is the primary thing, actually, you know it very well. And the photovoltaics is simply photo means light, plus volt means current, electricity, and that is electricity generation. So this is simply a photovoltaic effect. How it is generated, why it is generated, now we will try to understand. This is the historical thing, which is starting in long back, about let's say 180 years ago, about so in 1839. So this is the history I just put for your record. Now, this is actually, I hate this animation. I always used to have everything on a screen so that we can talk of this. So the photovoltaic effect, if you go to the previous slide, again, this is, you see that 1960, it is photovoltaic. It is in 1954, the semiconductor junction, it was observed. So now how it is working, just a small, I would like to, let us say that you have a p-n junction. This is the symbolic representation of p-n junction, where in a p-type material, you have these holes, and they are associated with the nucleus. Why it is minus sign? Because when any hole leaves the atom through which it is associated, that atom will be negatively charged. This is why this is minus. Similarly, these are the electrons, and there is a positive nucleus, you can say, or positive atom. So positive atom, why? Because the electrons, when they leave, actually, then the atoms would be positively charged. So this is why this is positive charge. This is very simple thing you understand from the 10+2 class, but still I found in various stages, still they have doubt how the p-n junction, why it is so like this. When you see that this p-n junction is formed, and this is the energy representation. There is a valence band, conduction band. This is the EI, that is the pure energy level, and then the Fermi level for the p side. EI represents basically the intrinsic energy level. Okay, this is Fermi energy level for the p side. This is Fermi energy level for n side. And when the junction is formed, p-n junction is formed, you see that these positive holes are on this side through the depletion layer, negative are this one, because this electron is going to this side and they are forming basically neutralizing. And why these electrons are moving? It is only because of the concentration gradient. Similarly, the holes are moving because of the concentration gradient. So you see that, and in this region, there are two types. Always remember that there are two types of current. One is because of the diffusion, which is because of the concentration gradient, and this is because of this is done by the majority charge carriers. You always remember that in n side and p side there are minority charge carriers also, and when the minority charge carriers, for example, when the hole in n side, when it comes in the influence of this depletion region, you see that it would be a favorable field for this, and that hole will simply be drifted to this region, in the p region. Similarly, the hole, the electrons which are the minority charge carriers in the p region, when it comes in the influence of the electric field, this electric field which is due to the depletion layer, it is simply going back to this side, going to the n side. And if you check it with the majority charge carriers, this depletion layer is a kind of stopping potential for them. For example, you can see that holes, they cannot move this side because this is unfavorable field for them, because it is in opposite side, because holes are the positive charges in nature. And the electrons, when it goes to this side, again, it will not move to this side, it will be deflected back because this E field is true. There are two types of current, one is drift and the diffusion. So drift current is because of the minority charge carriers, and diffusion current is because of the majority charge carriers. So this is the one thing which you should always remember. Okay, so now what is photovoltaic effect? When you expose a kind of p-n junction with a light which has energy greater than its band gap, what would happen? That the electrons which are this side, in the p side, they will move to this side without any barrier, and they will collect to this side. Similarly, the minority charge carriers, which are holes in the n region. एक मिनट जरा सा मैडम, मैं क्लास में हूँ, जरा सा लेक्चर ले रहा हूँ, ठीक है? हेलो, okay, sorry. So you see that yeah. So here, when we expose this our material to the electromagnetic field, or let us say the light, which has energy greater than Eg, so that will generate. First, let us understand that that light will generate electron-hole pairs, and the concentration of electron-hole pairs which are generated, the electrons have it will only affect the minority charge carrier concentration, because they are of the order of 10 to the power of 11 electron hole pairs per centimeter cube, and majority charge carrier concentration is about 10 to the power of 20. So the majority charge carriers is about 1 billion times more than the minority charge carriers. So it will affect this light will affect only the concentration of the minority charge carriers, not the majority charge carriers. So when the minority charge carriers are excited in the p and n regions, what would happen? That they will flow automatically to both the sides because of this favorable field. So the electrons from the p region will be collected at this n side, and the holes from the n region will be collected from this side. So there would be electrons and pylation of the charge carriers, opposite charge carriers on both the sides. So you see that next condition. So this is simply the energy diagram where it is shown that the electrons from the p region, they will simply go to this side, and the holes from the n region, they will simply go to this side. However, the majority charge carriers will not be affected, and and they will simply drift away. They will be returned back to their own region actually. So you see that, yeah. So when this is exposed to the, this is exposed to the light, the electrons will be, which are minority charge carriers in the N region, will be collected on this side, and the holes will be collected on this side, accumulated, I mean, in the presence of the light. Now, when you connect it, this region, to a simple wire, then what would happen? That these holes or these electrons will flow through the wire and they will come to this side. So you see that the electrons is flowing. The electrons are flowing from this region to this region. So the current would be flowing from P region to the N region because it is opposite to the motion of the electrons. So what will happen that the current is flowing from the positive region to the negative region. It is simply working as a cell. When you take a cell, so you have a positive terminal and you have a negative terminal. When you connect it with some resistance, what would happen? That the current will flow from the positive region to the negative region. Okay, so this is simply working as a cell, and this is why it is known as a solar cell or a photovoltaic cell. So photovoltaic effect, what is photovoltaic effect? It is simply appearance of forward voltage across an illuminated junction, and this is known as the photovoltaic effect. So this is happening only in the presence of light whose frequency is greater, whose energy is greater than Eg. If it is so, then only you will be able to get the current. Otherwise, if Hν is less than Eg, in any condition you cannot get the current in the external circuit. Okay. So this is simply the IV curve I would like to show. This is, you see that the first line, this line is showing the current in the forward bias condition, and this is the reverse current. This is the dark current when there is no light. When you put the light, what would happen? That put the light, the reverse current would be increasing because of the generation of the minority charge carriers. So you see that this is increasing in the negative side of this I-axis. Negative side, and when this is the light generated current basically, and when you increase it and you go to this region, so this is simply going to this side. So in fourth quadrant, you see that in the first quadrant, if you can take V and I, so the power which is generated, that is V into I. Simple mathematics of earth class. The power is V into I. So here, whatever power is generated, you see that in this quadrant, in the first quadrant, I mean, the power is V into I. So V is positive, I is positive, so the power is positive. In the second quadrant, there is no VI, so leave it. In third quadrant, again, you see that V is negative and I is negative. So again, when you calculate power, this means that it would be positive. Minus into minus is plus. So minus I into minus V is plus VI, which is power. Now, when you take this fourth quadrant, what is happening in fourth quadrant? In the fourth quadrant, V is positive, but I is negative. So when you take a multiplication, it would be negative power. So what is the meaning of positive power and negative power? Positive power gives you that when the device is connected to any circuit, it consumes power from the cell, from the source actually. So this in the first quadrant and in third quadrant, it is simply working as a device which consumes power from the energy from the source. However, in the fourth quadrant, the power is negative. So this shows that it is, instead of consuming power, it is doing the reverse thing, that it is delivering power to the system. So in this quadrant, it is working as a cell because it is delivering a power to the system. So the external system. So this means that this is a cell. So in the fourth quadrant, it is working as a cell. So I would go to the next. So it is simply a kind of photovoltaic cell, and the photovoltaic cell is known as photovoltaic when it is working in an ordinary lamp, which you produce in the lab actually. But when you put it in the solar radiation in the sun, then it is a solar cell. So photovoltaic cell is the cell when it is working in a lab with the appropriate the illumination, and if it is working in the ground, on a ground with the sun, then it is a solar cell. So this is some fundamentals I gave you, and this is the basic structure of photovoltaic solar cell, which you have. There are three components: light absorber that absorbs, carrier collector that the light absorbers absorb and generate carriers, charge carriers. There are charge carriers collector which captures the carrier and move it to the external circuit through the metal contact. So this is simple three components you need to make a solar cell. So this is the IV curve which I showed. Actually, I have just inverted. This is the minus I axis. It is inverted to the positive side just to show it in a proper way. So I is a negative I axis. So you see that this is that part. Yeah, this part, the fourth quadrant. So this I was inverted and this phi is in this side. So V is same. So I have just inverted this through by 180 degree. So this portion I am showing actually. So there is this curve which is shown, and this is the short circuit current. Then this is the open circuit voltage, and you have short circuit current. It means when you connect it, the negative and positive terminal, that is P and N terminal, with simple wire. So it is short circuit. There is volt potential would be 0. So corresponding maximum current you will be getting. So this is the short circuit current. When you put it open, just without disconnecting, so the maximum voltage you will be getting. At that time, no current will flow because there is an air gap between the two terminals. So this is VOC, which is the maximum voltage you can get, open circuit voltage. When you try to calculate on this axis power, so when you maximum power would be ISC into VOC, but when you take ISC, so VOC would be equal to 0. So the power which is being delivered is ISC into 0, that would be 0. Similarly, when you take VOC only at this point, ISC would be 0. So the maximum power at point will be getting at PM, where corresponding I is IM and VM. So this is the expression for the electricity, the current which is generated. This is the diode current, and this is the light generated current. So this is diode current and light generated current. When cell is short circuited, as I said, that V is equal to 0. So this is I is equal to minus IL, because diode current would be 0. So that is the IS here. When the cell is open circuit, when I is equal to 0, so this total I, when you make it 0, so you will be getting this expression which is corresponding to VOC. The parameters which we can get here, you can see this is the maximum power which is generated. This is VM into IM, and there is a fill factor which is defined. Fill factor is the corresponding to ISC and VSC, which is the maximum power you can have the values. If VOC into ISC, when you compare it, the maximum, so this is the fill factor. And efficiency of the solar cell is defined by the maximum cell which is generated, power which is generated, and incident light intensity. That is simply output by input. This is the output VM into IM, and the incident light intensity P in, which is dependent on the solar insolation, the area of this, and other parameters of the cell. Of course, the Shockley and Quasar actually SQ limit, they prove that in short, I would say SQ. This is the Shockley and Quasar. They showed that for a PN junction, the maximum solar conversion efficiency, it can be up to 33.7% by various calculation. This is the theoretical calculation. By assuming that sun and cell, they are the kind of black bodies, the sun is delivering power, and the your cell is receiving power as a black body. So this is the thing. The relation of the maximum efficiency with the band gap, this one, so maximum is about let us say that 1.5, 1.4 and 5, the efficiency is maximum. So 1.4 and 5 electron volt, a corresponding wavelength you can always calculate by energy Eg is equal to Sc by lambda, or h nu. So nu and lambda can be calculated. The factors, they are affecting the efficiency. Of course, the cell temperature, higher the temperature, efficiency would be lower. The energy conversion efficiency, it is required actually on the many parameters. They are dependent on the reflection, the charge carrier conversion, they are the trapping of the light. So all these things, absorption of the light, all these parameters, they are dependent. Okay, so as I said, the maximum power we have already defined, so there is no need of again redefine it. Till now we have come across the 3 generations of the solar cell. We have crossed, actually we are at the 3rd generation. And then in 1st generation, we had a mono crystalline silicon, polycrystalline silicon, multi-junctional cell we had, and these are the highest efficiency which we could approach actually. Okay, thin films later on from the bulk to the thin films, that was the amorphous thin films, the silicon, cadmium telluride, and copper lithium gallium selenide with this efficiency. In the low cost and high efficient, now we are looking for the low cost and high efficient system. So this is dye synthesized solar cell, quantum dot synthesized solar cell, organic photovoltaic, polymer hybrid, and the perovskite solar cells. So these are the things which we are in the 3 generations. As I said that the 1st generation, they have the crystal, single crystal and multi-crystal solar cells. They are simply the PN junction. So the advantages was for them was the broad spectral absorption range and high carrier mobility. And here disadvantages was most of the photon energy was wasted, and of course you need to have single crystal if you are using, and the single crystal is quite expensive, so that needs a kind of manufacturing technology that is more, so that makes it more costlier actually. The 2nd generation solar cell, as I said, that we use a kind of thin film of the silicon and the solar cell, the cadmium telluride, silicon, this carbon CIS, and all these thin film solar cells we used actually in the 2nd generation. The advantage was, of course, the low material cost, reduced mass. But of course, the cadmium telluride, they are the scary materials and the toxic type thing. So they are the disadvantages actually. Okay, so in the 3rd generation solar cell, you can see from the graph that this is the 1st generation, the 2nd generation, 3rd with the efficiency and the cost in US dollar. They are, of course, the 3rd generation, they are highly efficient as well as, but the lower cost as well. Here, the 1st generation, it has the lower efficiency, but the higher cost. And the 2nd generation, of course, because of some disadvantages, they have the limited reason with of course, the lower efficiency as well as the, of course, relatively higher efficiency, but the lower cost. Okay, so this is the current status of the solar cell devices, materials, in fact. And you see that these are the different materials which are being used, and you see that this is the number of years they take. You see, 1975 to 220 many. They took a flat linear region and very slow rate growth to approach to the high efficiency. This is the efficiency you can see. Now I would show you this the kind of perovskite materials, and they are started in 2009 actually, and 2014 the first paper came, and up to now they have very exponential growth. Sorry, this one. Yeah, this one. You see that this is the very exponential growth for the perovskite solar cells. So the people, when they came across about the perovskite solar cell, they found it very attractive because it is lower cost, and it is giving more and more efficiency, the high efficiency for that. I would also come to the problems associated with this. it is said why perovskite. Okay, so the perovskites, they have the high charge carrier mobility, long charge carrier lifetime, high open circuit voltage, band gap, the tunable type of band gap, and low cost fabrication. You see that here, when we talk of photovoltaics, we all in the beginning we talked of the semiconductor. We had a PN junction, but here there is no junction actually. So what is, as I said, there are materials. This is the whole transport layer. This is the electron transport layer. They are the carrier capturer actually. And this is the active layer, which are basically the the perovskite that generates minority charge carriers. Okay, so if there is no junction, then what type of matching we need actually? So that is the kind of energy band alignment scheme. The band gap, the band energy level of band gap of the whole transport layer should match with the active layer, should match with the electron transport layer. If it is so, then only electron transfer and the whole transfer from the active layer to the electron transfer layer and the whole transfer layer can take place, otherwise not. So this is the perovskite material, the whole transport layer. This is the electron transport layer, and they are the as I said, that the another thing is the electrodes, that is the capturing the electrons and holes. As I said, that this is the solar cell configuration. We have active layer, high transport, the whole transport layer, and the electron transport. These are the materials which you can utilize for this configuration. This is the schematic diagram once again, which is showing the different layers. This is the perovskite, which is the active layer, whole transport layer, electron transport layer. They are the TCO, that is a kind of base material, and this is the glass, and then the contacts, which is required to connect from the external circuit to flow the electrons and the current. Perovskite is simply a kind of AbO3 material. As I said, that now the task is to talk about the more and more about that material aspect. So I'm approaching to that point. So you see that we have a kind of AbX3 material where A is simply CS3NS3 and Ma. That is CS3NS3 is the methyl amine, which is Ma plus, which is known as form a medium. This is the CHNS2, this is Fa plus. Then cesium is also used, and this A, when we use AbX3, B refers to lead, Sn and Ge. Mainly people are using lead. And lead is, you know, that this is the hazardous material. It says not recommended, and this is one of the major problems that people are facing. They want to replace lead actually. To replace lead, we can use Sn or the germanium, Ge. Okay, and X is simply halide anions such as chlorine, bromine, and iodine. So this is AbX3 type of perovskite, which is being used nowadays for the perovskite solar cells. I think this is simply the band alignment, the electron transport layer, the perovskite layer, and STL, the whole transport layer. The band alignment is given. Perovskite active materials. This is the graph which is showing that up to what frequency region you need more and more absorption coefficient. So you can see that absorption coefficient is higher, above 1.5 electron volt. So more and more energies, the solar radiation is absorbed, more and more electron hole pairs will be generated. Probability of generation will be more, of course, and then there are many other factors also, not only the generation of the electrons only that is required, the electron hole pairs, I mean, but you have to stop their recombination also, which is the major problem nowadays. So efficiency with the band gap, you can see that SQ limit everywhere, and here the photon energy, and then the absorption coefficient. Lecture chal raha hai. Kuch jari hai? This is the time. This is the PL study that shows the normalized value of PL and then time of excitation. So all these, for the good materials, you need to have high conductivity with electron mobility, uniform thin layer, chemically stable, hydrophobicity, semiconducting index, all these properties you need to have a good absorbing material. Now, what is the present scenario? This is rather old data, 2 years ago. Number of publication, you see that 2009 I started, there were 1 publication, and it is continued on increasing. I forget to include the new data. It is exponentially, more than exponentially increasing basically. Okay, so you can see this data, the power conversion efficiency with the area, with the different years, it is also increasing. As I said that the first paper published in halide perovskite solar cell in 2009. This is the result for CS3. This is the NS3 PVBR3 and TiO2, and this is the photo current that showed here. And this is just a kind of advancement, and this one. So this is the work he used, kind of this one, and then. You can use this one-step deposition method of lead iodide perovskite solar cells, and when you use it, you can see this how much current density you can get with. All are increasing, and with the wavelength, this is the data which is shown, and this is of course the reference I have given below, you can look for. Of course, this is the development which I want to show you for the different materials, and this is CS3, NS3, PVII3 for the perovskite solar cell. These are the data which is showing with the current values, with the number of devices, which is with the efficiency, because the main issue is with these devices are the durability. They are not stable. I mean, even sometimes they are stable less than for 1 day. So even though if it is showing very high efficiency, if it is not working for a longer time, it has no meaning actually. So the different synthesis approach has been adopted to keep this material more and more stable. Okay, so these are the efforts. Wait, so this is the major issues with the perovskite solar cell. You can see that large number of efforts have been made to develop a promising active material, and you see that this man is fixing all the pillars with the efficiency, but the stability is not being fixed at the moment. They have the light, heat, humidity, they are pulling down to fix it. So we had to consider all these things to make the material more and more stabilized. And what we can do, we can choose, we have options of various materials, you can go through that. And what are the problem with this? These materials, they are heat sensitive, light sensitive, oxygen means the moisture, and then air also. So this is particularly for methylamine PBI3 material, which was the published in a very first time. So they are the possibilities. You choose different materials and try to stabilize, to fix this pillar in a stable form. The people are working. So progress in performance showing the ability. So this is what we are trying to do. And in this line, to make it more and more stable, what works have been done. Let us say that MaPbI3, this is when you use halogen anions, you replace I with Br and Cl, you could get more humidity resistance, and light resistance, humidity resistance also. But other problems remain same. A site substitution means you reduce Ma with some Fa, Cs, cations, and this one. So there are the heat resistance, humidity resistance, humidity resistance, and then these are the things which you can put in a advancement or as advantage of the substitution, but the other pillars like humidity sensitive, sometimes heat, sometimes moisture resistance, all these are still there, the oxidation resistance, oxygen resistance. So these are the things, again, they are in pipeline. So this is the example of the A site substitution, where the CS is replaced with MA with some fraction, and these are the data which is reduced with the different X value, and this is found that it has higher efficiency with different, you see, time in minutes. It is given in minutes, not in a day, even not in a year. So for a minute you cannot use solar cell. But of course, the science is working very slowly, but of course it would have some milestone to reach, and once it is reached, of course everything will be materialized in a proper way with the high efficiency. These are the data which I would like to show for some of the A site substitution. Again, these are the data, XRD data, absorptance, and the current density with this energy and the efficiency. You see that this is absorption in the arbitrary unit, and then these are the data which are shown for the CS substitution with MA. Again, A site substitution with the different possibilities, FA, MA, PB, sorry. Yeah, and with this the efficiencies, perovskite cell efficiency with the different substitution is given here. You can see up to 16% we could reach maximum, and with the different substitution you can see also that how the PSC is affected with time. So all these works are in progress. Again, A site substitution, you see that when you use CS, RV5 CS, and then something is good, but at the same time, something is also down. So some quantities, for example, enhancement of the charge mobility was down in this case. Both are good, but of course, there was problem with the humidity. So all these problems are there with the perovskites. Why? But still it is more attractive because it is showing high and quite cheap also, high efficiency and quite cheap also. This is why the people are working in this field. Now ABX3 X type, the X site substitution, where the X is basically halide materials. So different halide materials are used, and for this substitution, for example, you see that this BRX, PB is substituted with bromine, and this is the calculated with the efficiency. For X it is increasing, but here with X is equal to this one, it is maximum it is obtained. This is the stability of the material which is shown here. The energy, band gap energy is also shown here. The current density is shown here with the voltage, with the different substitution of X, that is the bromine. Again, next time, few data on the X type. X site substitution, that you see the I is replaced with this SCN, and then this is the these are the data. So as I said that when you take ABX3 type of material, where A is MA, B is this lead, and X is the halide materials. So in that condition, you have all the possibilities of substitution, and you can include more and more things to substitute, so that they are giving you more stability and the high efficiency. Again, some data with the B site substitution, where B means lead is substituted with CS, with GE, with GE here, okay, with GE here. And these are the data which is shown for the different type of B substitution, B site substitution. Increasing efficiency with compositional engineering, you see that this perovskite solar cell efficiency with the year, so far we could reach up to about 25%. You see 23.7%, and this is 2019. The recent is about 5.3% we could reach with the perovskite solar cell. So the people are, this is again still in infancy state. People are working to stabilize these materials for longer time, so that it is, once it is done, of course, that would be, our life would be quite easy and the cheap, because you know that when you want to have some device in the market, you have to compete with the price also. So if price is high, it would not be attractive for the common people. Common people will not be using. So this is the compositional variation in the perovskite. You can see data that these are the possible substituents you can take. The red one is the more light conversion. So you can see the carrier dynamics. The carrier will be affected. The charge carrier will be affected with this color. The film morphology you can change with the green one. The phase stability. So all these possibilities, these issues are handled with this type of substitution. Okay, so this is the material complexity, and they are means different materials you can use to stabilize, as I show here in this periodic table. This is a kind of the comprehensive study for the electrode materials, organic perovskites. This is the very good data. You can see that efficiency is this tree, and then with the CSPVI2 PVR, with the CSPVI3, with the CSPVIBR. So all these branches, and you can see that they have different efficiencies, and this is the limit, which you can see that 24.75% with this CSPVI2BR, CSPVI3, you can go SQ limit up to 28.6%, 684%. So this is very a kind of illustrative data that you can choose your different materials for the whole transport, for the electrode, carbon electrode, for the organic type of whole transport materials. So this is a kind of survey you can find in this nanoscale paper. Again, the structural and dimensional engineering you can do, change the structure, change the by just composition, changing the composition, changing the dimensionality, 0 dimension, 1 dimension, 2 dimension, and 3 dimension. So this is the data for that. Again, statistical analysis. These are basically the data I'm providing you with the different VOC. You see that number of layers. If you enhance that, how it is changing the open circuit voltage, the short circuit current, is the cell efficiency, how it is changing with N. You can see over here the 2D perovskite, 3D perovskites, and the number of layers of 1D, 2D, 3D, how you are changing, and how it is the different parameters are affected. These are the materials with the different materials, which is shown here. And then this is the efficiency. This is the short circuit voltage, short circuit current, open circuit voltage, fill factor, and in which year they are shown, and they are the references. Okay, so this is the whole these are the few materials which is used for the whole transport material. These are the few materials for the electron transport material. So this is all about the solar cells which I spoke, and the photovoltaic cells which I spoke to you. And this is one of the major means you can say the replacement for the fossil fuels. Nowadays people are working, and then we can have a kind of clean and green energy using those materials. Now I will start to the new topic, which is another type of material, and entirely different than the solar cell. But just take a break of 1 or 2 minutes. If there are any question or any doubt regarding the previous topic, we can have a discussion on that.
Thank you very much, for your nice talk. Now the session is open for the discussion. If any query, any doubts or any comments from the participants, please unmute yourself and put the questions before the speaker, sir.
Okay, so yeah, any
Yes,
question?
please. Please go ahead. I think things are clear.
Okay, so now I would cover, actually, I was told and means I thought of talking, in fact, the materials for clean and green energy. The first topic I covered is solar cell, so that I covered from the materials aspect as well as from the fundamental point of view. Now I would give an idea of entirely different material, which is nowadays people are working a lot, and for the green and clean energy point of view. So, okay, I would go to the next. Yeah. So this is the very famous experiment which is done about 2 centuries ago. You see that when we take this is simple electrolyte, the cell arrangement, and when we take a platinum electrode, okay, and this is the dilute acid electrolyte, of course, and you connect these electrodes with the battery. So the reaction electrolysis will take place, and then oxygen and hydrogen would be collected at the top of this tube, actually, this tube. So oxygen and hydrogen will be collected. What happens? The people thought after about a century that what happens if we, instead of connecting the current, the battery to this system, what happens if we give hydrogen and oxygen? Can a current be generated? It reverse. They thought of its reverse. So what they thought, that again you take the electrolyte, some weak acid electrolyte, you take it, and here you put oxygen and hydrogen, and when you try to connect it with the ammeter, they found it current through it. So this means the reverse is also true. So what we can do, we can give oxygen and hydrogen to some of the materials to do both the sides, and there is some electrolyte in between, so current can be generated. So this means that hydrogen and oxygen, they are working as fuel to generate that current, and thus since it is generating a current, so it is known as cell. And since it is generated by fuel which you are providing, so this is why it is known as fuel cell. So you have a fuel cell nowadays, which is very, very important in research point of view, and it is already in functional condition in advanced country like Europe and US. And we are in our country also, the people are working in this field in a very fast way, and it is rapidly growing. And fuel cell running buses will be shortly on your road in future. So this is simple the thing for the fuel cell, where you give at the electrodes, the anode and cathode, you give oxygen and hydrogen, and you don't need to do anything. And the external circuit, you will be getting a current. So the fuel you supply, current you are getting. So this is why it is known as fuel cell. So this is simple function. A kind of, you see the anode, which is, and cathode, they are the electrodes. And you have hydrogen fuel at one end, and at the cathode you simply supply oxygen. And at anode, the hydrogen is connecting with the hydrogen is converted into hydrogen ions, leaving 4 electrons. And then these the electrons are coming to the external circuit, where you have something load which you collect to so that current can flow, and it is connecting here the oxygen you are supplying. So these 4 electrons are captured by hydrogen, these oxygen, and they are generating and this 4H, the ion, which that is flowing through the electrolyte, leaving this region to the cathode, and they are combining, that is the 4 electrons, oxygen, and these 4 hydrogen. They and water is
Prabhakar ji, you are muted, sir.
so why I become muted? I don't know. I never from my.
That was some network issue, maybe. Please go ahead.
Oh, so are you able to see this slide?
Yes, no, slide is not visible. Please.
Okay. Is it visible now?
Yes, yes. Now it is visible.
Now it
The
is.
previous slides you could see or not?
No.
Oh God.
We have just from the layer of hydrogens.
Just a minute. Did you see this one?
Yes. That was it. It is 58. No, 59. Please go. Yes. We have seen up to that.
Okay. So this is So this is
Okay.
different types of fuel cells.
Yeah.
And they are basically polymer electrolyte membrane fuel cell, alkaline fuel cell, phosphoric acid fuel cell, molten carbonate fuel cell, and solid oxide fuel cell. These cells are named based on the electrolyte material which you are using actually. For example, in the polymer electrolyte membrane, they are the immobilized acidic polymers you use as an electrolyte. For example, solid oxide fuel cell, you use doped and co-doped ceria and yttria stabilized zirconia. So different electrolytes you are using, and this is the operating temperature actually. So the operating temperature for polymer electrolyte membrane fuel cell is from room temperature to 200 degrees Celsius. The alkaline fuel cell, the room temperature to 200 degrees Celsius, phosphoric acid fuel cell 160 to 220 degrees Celsius, 100 to 620 degrees Celsius. This is the operating temperature. Means you need to have this much temperature to operate actually. Okay, solid oxide fuel cell. Just a minute. Okay. Extremely sorry. Actually, there was some important call which I needed to.
Yes, no
uh,
problem, no problem. Please,
and
please go ahead.
I could not have avoided that. So
Yes,
sorry.
yes, 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 we
So,
understand.
so again, I will share. Actually, this is working day, na? So in working day, it is always there are
Okay,
a lot of works to be done. So.
definitely.
Again, so you see that this is the simple chart that's showing that the operating temperature, and you see the efficiency, very nice efficiency you are getting in comparison to the solar cells. They are up to the 50% and 60% in the case of solid oxide fuel cells. So you see that what are the fuels you apply and the fuel reaction substance, and then the electrolytes which you are using for, let us say, solid oxide cell. The electrolytes are, as I said, that doped and co-doped ceria, molten carbonate, the molten salt. So you see that these are the different electrolytes. They are different anode, the cathode materials. So this is simple a kind of battery you can use. You can stack many layers, and you have arrangement of the fuel supply, and then in the external circuit you will be getting simple current through that. Of course, there are a lot of technological aspects from the physics and chemistry point of view. It is very easy to give the theory, but to implement it, many engineering processes are required. So, and this is one of the kind of problem. So you see that I'm talking of the solid oxide fuel cells because it has the highest efficiency, and the only drawback is it needs a very high temperature to to get it operated. So you see that in fuel, in this case, you need to have the hydrogen with the carbon dioxide, and as a fuel they are giving, and the anode, at the anode, this hydrogen is connected, is interacting with the oxygen ion which is coming from the cathode through this electrolyte material, and when it is it is reacting, this leaves 4 electrons and water, simple pure water. So these electrons are going to the external circuit, giving electricity, and these electrons, they are returning to the cathode, where you have a pure oxygen or simple air oxygen, which is generated, which is reacting with this electrons and leaving 2 oxygen ion. And these again oxygen ion is moving through the electrolyte material, so that it can interact with the hydrogen at the anode. So this is the complete circuit, and the simple, you keep on supplying hydrogen and air, or hydrogen and oxygen at the 2 electrodes, and at the external circuit you will be getting the current. So this is a simple working of a solid oxide fuel cell. All oxide all fuel cells work in a similar fashion, only the electrolyte is changed, and in some cases it is the oxygen ion which is moving, some cases it is the hydrogen ion it is moving, some cases it is different other ions which are moving, depending on which type of electrolytes you are using. In a solid oxide fuel cell, it is kind of electrochemical conversion device that produce electricity directly from oxidizing a fuel, and is characterized by the use of solid oxide material as electrolyte, as I said. The application, you can have a portable power source for a small scale application, auxiliary power source for the light weight unmanned vehicle like drones and something like that. It has very high efficiency, fuel flexibility, environmental friendly, and low operation cost. Advantages of the solid oxide fuel cell: it is high electric conversion efficiency. As I said, it up to 60%, more than 60% most of the times. Cogeneration potential, high quality exhaust heat for heating, cooling, additional power generation, high environmental performance, of course, fuel flexibility. Size flexibility means you can make it in a different size and different design, actually. Load flexibility and the multiple market applicability. So these are the advantage of this one. Now, as I said, that it contains electrolytes and the kind of not only electrolyte, but the electrodes also. So an electrolyte is the major component of any any fuel cell. So the electrolyte should be dense, of course, to prevent any short circuit between the electrodes. It should be stable, both in reducing and oxidizing environment. It must have sufficient ionic conduction so that the oxygen ion can move from the electrode to the from the cathode to the anode. So it has good oxygen ion transport. So it should be oxide ion conductor instead of electronic conductor. And electronic conduction should be as low as possible in order to avoid any leakage current. And uniform thin layer it should be required. You see that the factors which are affecting the ionic conducting of electrolytes, that should, you see, you can change microstructure, you can change processing technique, you can change composition just to affect the conductivity. Ionic conductivity depends on mobility as well as the concentration, mobility of the charge carrier as well as the concentration of the charge carrier, and that you can convert by composition, microstructure, and processing here. So this is what the different type of composition, the composite materials, disorder lattice, isolated defects in yttria stabilized zirconia, doping in yttria stabilized zirconia. So they are just to change the mobility. So these are the kind of summary that how you can control the conductivity of a electrolyte material to put higher and higher side of oxygen ion conductivity. You see that this is the number of publications which are coming on the electrolyte materials, publication on the electrolyte. So this is many people are working on different type of electrolyte materials. In our lab, we have worked on various materials, which are for the electrolyte point of view, this is the fluoride structure, perovskite structure, LaMOX family, composite electrolyte materials, NBT and YGO. So different type of electrolyte materials we have worked on. And this is the summary of all the things. You can see that this is the result from our lab where we have characterized the conductivity, and we proposed that basically the composite material with the LSGM, which is lanthanum gallate material, having strontium and magnesium doping, with the yttria stabilized zirconia with 9:1 ratio, it is showing the highest conductivity. And this is the conductivity. It is, I think, the maximum conductivity so far reported for any electrolyte material which are working even in the currently fuel cells operating condition. The anode material, in our lab also we have worked on the anode material, so it should be very good electronic conductivity. Now it is not needed at all in the oxygen ion conductivity. Ionic conductivity, it should be low, it should have low ionic conductivity, it should have electrode resistance which is less than this value 0.15 ohm. Thermal stability, it should have chemical stability. Thermal stability is very important because, and thermal is not only the thermal stability, but thermal compatibility of electrode, anode, and cathode is required. They should have, because it is operating at very high temperature in the range of 600 to 1000 degrees Celsius. So if something is has more thermal expansion coefficient than the another one, so there would be crack which is generated. And that leads to a problem in the operation of a solid oxide fuel cell. So when you choose a material aspect, you have to think in this direction also, that anode, cathode, and electrolyte should have almost same thermal expansion coefficient. So this is the these are the properties of the anode materials. We have worked on in our lab perovskite materials, the strontium titanate based system, double perovskite materials, and electrolyte system in the perovskite materials. There's strontium SrSiO3 based system. So this is few works in our labs. This is the range of conductivity which is shown for this. I think this is the calcium doped material, which is showing the highest conductivity, and it is very good durability also. We measured it in the hydrogen atmosphere. You can see this data is shown in the hydrogen atmosphere. So good conductivity was reported from our lab in the different materials. Now we also worked on few cathode material. This needs a very good electronic conductivity. As I said, that thermal expansion coefficient should be matched. It should have enough porosity to allow to diffuse oxygen through cathode. Of course, anode and cathode, both should have the good porosity. They should not be very dense. Otherwise, the hydrogen gas from the anode side and on the anode side, and oxygen gas on the cathode side will not be able to react, not be able to reach at the reaction level. So they should be porous in nature. Of course, for the cathode, the stability under the oxidizing condition, atmosphere, and high catalytic activity for the oxygen reduction reaction, so that the oxygen can be reduced in order to generate the oxygen ion. So we also tried to understand the kinetics of cathode material, where the oxygen gas is converted into the oxide ions actually. So this reaction basically it occurs at the triple phase boundary, and this I would like to show in this schematic diagram. You see that electrodes are here, and there are three mechanisms through which this oxygen is adsorbed at the electrolyte, at the electrode, that is the cathode, and it is converting the oxygen ion. One is at the bulk, and another one is at the not at the triple phase boundary at here, and one is at the bulk, and one is at the bulk and the interface, electrolyte interface surface path. So in this condition, the three types of mechanism are proposed, and via 4 electrons process, via 2-step pathway, and mechanism via 1-step process. So these are basically the reactions which are possible, and for different materials, depending on the good electronic material, depending on mixed ion conductor, or simply the electronic conductor, we can get these mechanisms. We use sometimes the more chemistry, sometimes also the cyclic voltammetry, where we use to characterize the ORR reaction, and this is the simple arrangement of cyclic voltammetry in our lab. We use kind of reference electrode, we use working electrode, which is our sample, and we also use a kind of the reference and the working electrode, and one more electrode that I'm missing the name actually. Okay, let us say that the 3 electrode. Okay, so this is this we are using, and we always calculate the current as well as potential. So with the increasing current potential, first the current increases, there is a peak, and then again there is a reduction in this current, and when you reverse the voltage, the reduction continues, means that you reduce the voltage, they are following a kind of reduction in current, which is usual. There is a peak in negative side, which is the cathodic reaction. This is the anodic reaction, and this is connecting again. So this is a kind of duck shape characteristic is observed. This is result in our lab, where we use PRBaCO2 material, where we prepare the system in 2 ways. One is through the solid state reaction, and one is through the combustion reaction. And we propose that the solid state reaction method is is more suitable for the cathode reaction and for the system to be operated as cathode. So this is a kind of the two different samples. One is solid state reaction SSR, and one is ACR, that is the combustion reaction, auto combustion reaction. And this is the data for the conductivity. In SSR, we got more conductivity rather in comparison to the auto combustion reaction. The ORR reaction means that is the oxygen reduction reaction, which is required for the cathodic reaction, which is good. We found for both the system, which were prepared through SSR and ACR, you can see in the circle. This is again when the addition with the, you see that X is equal to the different X. When you increase the X value, this means that you are increasing the PR content and you are reducing the BA component, the content. So when we did it, so for X is equal to 0.6, we got the highest cathodic reaction, that is ORR reaction. You can see this area is more than the other values of X actually. So this is, and this is at the different rates. And again, this is the, in fact, different system, because this is the PR, this is double perovskite, and this is SM2 minus X SR. Here we took one system where when we added an SR into this system in the SM, and then for different X values, we calculated the different values of current density with respect to the reference electrode. And then we found that they are showing a good cathodic reaction for this system. This means that the oxygen reduction reaction is very good for different values of X. So this is, you can see that for X is equal to 0.6 and X is equal to 0.1, these two data are given here. This also indicates that when we got this current JP, which is the peak value for different rates, we found that the slope is greater than 0.5. So the fundamental, we can also conclude that the more, if the slope is more than 0.5%, the process of conductivity is through the diffusion process. So now we worked on these materials, and this is, I think, with this note, I would like just to conclude with this simple picture. You have the way to go. One is going through this, you say that with the fossil fuels, which is going to this, the gaseous atmosphere, the hazardous gases, you can see the gateway of India, the India gate, where a lot of pollutions are there. So this is one way. And the another way is going to the clean and the green energy, using the solar cells, using the fuel cells, using the renewable energy resources. And this is this way. So now it is up to we where we want to go. And this is the responsibility of basically the scientific community as well as the technological community to give the pathway to the society, because after all, we all are working on the society, for the society. And we are the part of the society. So this is what the message is. Of course, everyone would like to go to the left, not to the right. In this condition, right is wrong and left is right. So with this is my group, which is of course old. Many people have left, and I think more than 6, 7 people have joined. So 3, 4 people left. So this is my group who are working. I presented the work of this Vani, who is nowadays in the IIC Bangalore, and some work of this this student. I'm missing the name actually. So this and Manisha, Ajay, yeah, Ajay, and then these are my 2 research associates, Pradeep and Priyanka. They are helping us in analyzing the data and experimenting the thing. So with this, thank you so much.
Thank you, Professor Prabhakar ji. You have starting with the very basic tutorial lecture for undergrad students, and they are very happy because they have revised their photonics, which is the part of their curricula, and the examination are going to start from 15th February in online mode.
Okay.
So they definitely they will be very happy and beneficial regarding the basics, and they also enlightened with the advanced topic for the PG students who are fully devoted to the PG and research. So they have scope, and finally they will decide to go on left, and that is the, that is the very need of time.
Yeah.
Now I request our faculty member Sai Kumar Chira, please propose vote of thanks to our speaker, and then the closing prayer of the day. And before going to hand over this to Chira sir, I also request to Professor Prabhakar, please, I have seen many faculty members from your department, and they are very, very well advanced researchers, and especially the field of biophysics and quantum information. We have started the biophysics as one of the undergraduate subject in UG level, along with mathematics and physics combination. So this biophysics at undergrad level is the only subject in our institution in this part of North India, except Chandigarh University. So there are many confusion among the students. What do you mean by the biophysics and how it is useful for the students who are especially doing with the mathematics group. So I like to request you, please convey my request to them to make some time after the end semester examination, which is going to be held from 15th February, and tentative dates may be just after Holi, that is in March. So I would like to request with those faculty persons who are having quantum information and biophysics.
Yeah, sure.
They are Professor Dr. Avinash Singh Parikar in biophysics and nanotechnology, and Dr. Rajiv Singh from quantum information and all. So
Certainly. I will say, and then we have also Professor Giri, who is working in the field of biophysics in a theoretical way, and
Okay.
Dr. Avnish Singh. There are two actually. One is Avnish Singh Parmar and one is Avnish Singh. So both are working. So Dr. Shraddha Mishra is also working. So I will. And in quantum physics, Dr. Sunil Kumar Mishra is also working along with the Rajiv Singh.
Okay.
So they will be helpful, and I will request them to contact. I will contact you through maybe Dr. Ashok Pathak ji, who is my colleague, and we were there in MSc together. So always pleasure to communicate with him.
Yeah. That's good thing.
Thorough gentleman, and
definitely he is our chairman in IQAC cell of this Autonomous College of Communication.
Coordinator.
And now I request Dr. S.K. Chira, please lead this the vote of thanks to the speaker and closing.
There is a hand raise, I think.
Umesh, yes, Dr. Umesh, please.
Yes, sir. Actually, it is not a question. It is just for sake of our young students that. First of all, thank you very much, sir, for very nice and very elaborative lecture, starting from very basics to the recent work going on in the solar cell, fuel cells, and many things. My question is just because this field is very open, and researchers are still trying to get improvement in the solar cells, fuel cells. So I want to ask for our UG and PG students, those who are interested to start their research work in this field, in the solar cells or fuel cells. So what would be your suggestions for them so that they shouldn't get stuck somewhere in meantime or during their research work?
Yeah, actually, this is very good question, and I think the students should be encouraged to start with the fundamental first, and then as I said, that there are many things to be done on the materials aspect. So they can try to take one component, because one person cannot make a complete system. So they can take one component of this and they try to optimize their properties in such a way that that is useful for that purpose. Right. So for example, you can work on the whole transport material, you can work on the active layer material, you can work on the electron transport material for the solar cells. You start with some already proposed materials, and you see that what are the shortcomings in those materials and how you can improve to get the required properties. So this is one way to do what I'm thinking. A similar thing is for the fuel cells. You can take different components, anode, cathode, and electrolyte, any of them, and then you can try to optimize the properties. And once you are at the advanced level, you can collaborate with some laboratory there. If they are working, let us say you are working on the anode, someone is working on cathode, someone is working on electrolyte. You can collaborate with that. You can share your results, and then you can have a complete fuel cell with these materials, and then you can characterize that. So this is what I am thinking, and this is what way we are trying to progress actually. So this is what I would say.
Thank you very much, sir. Thank you. Thanks a lot.
Thank you.
Okay, if there is no further questions, it is my great opportunity to give vote of thanks to Professor Prabhakar Singh sir for a delight lecture. Sir, you started the lecture with sure, pure, and secure. That's a great word to listen for this day. And we have a great visionary, that the vision you have to increase the solar panel, use of solar panel till 11% in 2030. Sir, we hope you will achieve, and maybe India achieve that great target. Sir, you also enlightened the students and MSc students especially with the photovoltaics and photodiodes and different generations of solar cells. And you have also shared the current work of the Parasite solar cells, and you have concluded with the materials for clean and green energy. That's great, sir. We are so thankful to you, sir. In spite of your busy schedule, you have allotted a time for us. And on behalf of students and on behalf of Even Christian family, we thankful to you for kind time and kind delivery presentation, sir. Thank you for being with us.
Yeah, thank you so much. And I think being as a teacher, it is my always duty to fulfill the need of the students. So I would be more happy if my lecture is useful to them. Otherwise,
yes, it's really very useful. You have mentioned very basic lecture details, and as well as current research work also you have discussed with our students. That is very great. And if no further questions, I would like to give the closing prayer. Let us look to the Lord in prayer. Loving Father, gracious God, we thank you for this beautiful and delight lecture from Professor Singh. Lord Father, whatever the knowledge he had shared with us, especially with our students, of Father Lord, it may be useful and helpful to the students to build our India with clean and green energy, of Father Lord. Lord, the vision that Professor Prabhakar Singh has, Lord, you bless him, anoint him with your amazing power and knowledge, of Father Lord, so that whatever the knowledge he had, he may share with research scholars, and may his research go well, and it may be, Lord, multiply, of Father Lord. We thank you that you have called him to be with us in this time, and we would be able to listen from him, of Father Lord. Whatever the knowledge that he had shared, that may be fixed in the hearts of students and useful for the future benefits of Father Lord. We thank you for all the resources that you have provided. In Christ's name we pray. Amen. Thank you, sir. Over to Dr. Anil, sir.
Thank you. Chiraji, now I request Dr. A.K. Pathak, if you want to say something to our guest.
Sir, actually, there is no limit of saying something for him. But the thing which I always prefer is that he always works in conjugation with his name also. If we know the synonym of Prabhakar, then you can know the direction of the working in the area, how the solar energy can be utilized. So actually his works in the direction of research also signify the direction of his name, and really I am grateful to have the association with a friend like Professor Prabhakar. Thank you so much, sir, for sparing your valuable time with us. And definitely we will, in future, we will again contact you for many more lectures. Thank you so much.
ठीक है, thank you, Dr. Sahab.
Thank you, Pathak ji, and please make continuous touch with the further course of action. And
Yes, yes.
thank you, Prabhakar ji, for being here. And
Thank
thank
you.
you all for our faculty member and students for joining this program and make success. Thank you.
Thank you, sir. Thank you.
Okay.
Thank you.
Namaskar.